This is example 8-6 about an airplane model. The idea here is that we have this model airplane and we have it in a wind tunnel with a wind speed of 450 kilometers per hour. And now we want to see what would happen if we did this test in water instead of air. And we're asked to find out what the speed in the water would have to be to get the same flow behavior. Now, if we're thinking about an airplane moving through air or moving through water like this, then of course the most important force is going to be the viscous forces, so we'll need to use Reynolds number. So let's write Reynolds number. Reynolds number. All right, we know that RE is equal to the density times the velocity times the characteristic length divided by viscosity. And now, of course, we know that for the flow behavior to be the same, the Reynolds number has to be the same both in air and in the wind tunnel and in the water tunnel. So if we say the Reynolds number for water would have to be the same as the Reynolds number for air, and we can write that as rho times V times L over mu for water equal to rho times V times L over mu in air, which of course means that we have a rho water, we have a velocity in water. Now for the characteristic length scale, we're using the same model both in the water and in the air, so we could just leave that as L. And then of course the viscosity is also going to depend on if it's water or if it's air. And the same over here. So we have density of air times the velocity in air times L divided by mu air. All right. So now we have our equation. All the densities and the viscosities we could look up, right? Because we're given that we're at 20 degrees centigrade. So that means we can solve this for the velocity in the water. So that means we get velocity in water, right? So we'd have to divide by rho water. So we have rho air over rho water. Then we have to divide by L. So we get L divided by L, that cancels out. And then we have to multiply by the viscosity of water, and we still have that one from before. And of course, let's not forget the velocity in air. All right, so we already know the L's cancel out, so it doesn't matter what the length scale is. We can now go and look up the values for the viscosity and for the density. We could also go straight ahead and just look up the values for the kinematic viscosity if we wanted to. But here we'll just stick with density and viscosity. So from table, whichever you want to look at 20 degrees C, right, we can say that rho air is equal to 1.202 kilograms per cubic meters. Our viscosity in air is 18.1 times 10 to the minus 6 Newton seconds per meter squared. And then rho water is equal to 989.3 kilograms per cubic meters. And then mu water is equal to 1.00 times 10 to the minus 3 kilograms per, not kilograms, it's not the density, Newton seconds over meter squared. All right, so now we have all our values and we can plug them in. So we get the velocity in the water would be 1.202 kilograms per cubic meters divided by 989.3 kilograms per cubic meters. The L's canceled out. So then mu, we get 1.00 times 10 to the minus 3 Newton seconds per square meter divided by, where's the other one? 18.1 times 10 to the minus 6 Newton seconds per meter squared, and then the velocity was 450 kilometers per hour. And that then means we plug all those numbers in, we get 29.935 kilometers per hour for the velocity of the water. Now it's pretty fast moving water, but we're in a water tunnel, so it is possible to do that. So with that, we found that if we want to take the same model and test it in water instead of air, then we'd have to have the water flowing at almost 30 kilometers an hour.